talk about our real material. So the first class for the chemistry I always do is introduction and review of our chemistry knowledge. This is we're going to do today and a little bit on Thursday. And Thursday we also do a review of some biochemistry knowledge. It's like a warm-up because you're coming from different background and your knowledge of chemistry will be different. So we want to make sure you have these basic knowledge. Okay, so let's start. My teaching style is that I'm going to draw on the blackboard, and you have your slides, but the slides and the blackboard usually is the same thing, but I use a different way to present. So we want to talk about is introduction of chemistry. So I always ask a first question. C612. What does this mean? Very simple high school chemistry question. What's a C?
Carbon.
Yes, carbon. What we call it? We call it's a skeleton of biological body. And you will see our major biochemicals, they are composed by carbon. What does this 6 mean? It is an atomic number. Then what does that 12 means? We call it a mass number. So far, if you can refresh this knowledge, you feel free to stay here. If you say that I don't know about this, then you can drop off the classes. That is a joke I always make because we have more and more chemists will be coming. Okay? So this comes out with our first question. If we have an atom, what will be the components inside? It will be composed by proton and neutron. And the proton, most of the time, is positive, and the neutron is not charged with anything. And in the middle is proton and neutron. How about outside? Outside, they're surrounded by a very heavy, cloudy area, we call. So we say it's an electron cloud. And the electron is negatively charged. So the total of the atom, it should be no charge. Okay, so let's review some of important biological activity atoms. So we'll say biological activity atoms. So what are the most important biological activities? H, hydrogen, carbon, C, oxygen, O, nitrogen, N. Of course, we need a phosphate, remember ATP, and we need a sulfide, S. Okay, we can draw a table. What is the atomic number? What is a mass number? And what is approximately amount in a biological body? Let's say in a bacteria. So atomic number of hydrogen is 1. The mass number is 1. Now why it is 1 only? This is one of the exceptions. For hydrogen, there is no neutron. There's only proton. So that's why it is only 1. How many percentage of that in a biological body? It's huge. It's 49%, close to 50%. The next one, carbon. Atom number 6, atomic number 12. How many percentage? About like 25%. It's also huge. How about oxygen? Atomic number 8, mass number 16. It is also 25. HCO, or we say CHO alone. This is almost 99% of a biological body. And we know that it will be composed to carbohydrates, will be lipids, and also will be major components of amino acids, further become peptides and the protein. Now, what is the nitrogen? 7, 14. How about phosphate? 15, it's a little bit tricky, 31, and the sulfide, 16 and 32. What's the percentage of these? Well, I will say accurately, depends on different products. It is about 0.1 to 0.9%. So these add up together somewhere between 99 to 99.9%. Now, where is the left? 0.1 to 1%. And we know our body needs some other atoms. For example, chloride. For example, sodium. For example, potassium and calcium, magnesium, ferric, ions, and all others. Okay, so this is our, basically we talk about the biological activity atoms. So we want to make sure something else, you know. This neutron, most of the time, the number is equal to the proton. However, there are some of the exception. For example, you heard about H3. You heard about iodine, 125. And you also heard about N15. What are these? We call these isotopes because they are offering different number of the neutron. And the isotopes, sometimes we also do a radio labeled. They become a radiation. So there is a very common old method called radiation immunoassay. This one could testing blood hormones all the time. Okay, another method what we can do is the electron. M15. This one, you should be relatively familiar with that. So if we draw this, it is a DNA. Remember, two very smart scientists, Matt Mendelson and Frank Stahl, back in 1951, they're using N14 and the isotope N15 do a hybrid and trying to repeat the DNA replication steps, generate more and more generations of spring generations. And what they confirmed? They confirmed the DNA semi-conservative replication methods, mechanisms, we could say that. Okay, this is something we just talk about the neutron. So we basically finished talk about in the middle. So we want to spend a little bit of time talk about this electron cloud. This is a huge topic. So I'm going to draw the line here. I'm going to move on to next section, a big one. That knowledge in a chemistry will be teach couple weeks. Lots of puzzles for that. We're just spending about 15-20 minutes to review it. So electron cloud, they are surrounded outside. And how they arrange, there are different rules to talk about that. So first of all, we have this atom in the middle. The electron outside is into different layer. We're using Arabic letters to say 1, 2, 3, 4, and 5. Corresponding to English letter is K, L, M, N, O. Okay? So basically we know the arrangement of the electron is from low to high energy. And overall, the electron has to be keep in a basic status because we try to low down the energy. We don't want to excite it. So therefore, come out with next question. Of these layer, there is have a sublayer. So this comes out with sublayer orbital. Now, how they arranged? What's the story behind that? We could give them an n number. This is the energy layer. And we'll get another number, which is L number. This is a shape of sublayer orbital. Oh, sorry, this is wrong. This could be sublayer orbital. So that's sublayer orbital. What is the equation for that? This L is equal or less than n minus 1. So let's talk about that. If n equals 1, what's the L will be? The L will equal 0. Therefore, what is the sublayer orbital morphology looks like? You learned in your chemistry class. It's a circle. We call it S layer because it's like a sphere. Okay, then let's do n equals 2. What's the L value will be? The L possibly will be 0, could be 1. 2 minus 1 equals 1. So what the sublayer orbital shape could be? Obviously it could be S. It also could be P. Then what's a P looks like? The P will be looks like a number. Because it's a number. So there are 3 directions. What are those 3 directions? It could be just straightforward perpendicular. We call y-axis. It could be laid down horizontally. Is x-axis. And it also could be a little bit slide. We call it z-axis. Okay, 3 different directions. Let's do more complicated. If n equals 3, what going to be the L number will be? The L could be 0, could be 1, could be 2. By the way, this is 1. Okay, this is 2. Of course, 0 is S layer, 1 is P sublayer orbital, How about 2? That's a D. Now we're not going to talk about this D to draw the figure because it's complicated. We just draw like this, and sometimes like this, like a flower, because it has 5 directions. Okay, let's go another one, more complicated. N equals 4. What's the L value could be? 0, 1, 2, and 3. Therefore, we got 0, S layer, 1, P, 2 is D, and 3 is F. How many directions of F has? 7 directions. That's more complicated. Okay, so since we see these mass and these morphology and the shape of the sublayer orbital of this electron cloud looks like it's complicated. Therefore, in the history, the physicists and the chemists worked really hard to find the way how they arrange. Therefore, it comes with 3 major rules. First one, very simple, minimal energy rules. This is we already talked about. When they do the arrangement, is always from K to O. Of course, there's more and more layer. From lower to higher energy, when they do the arrangement, they try to keep the basic status. Don't want to be excited about the electron. They want to make sure the whole energy is lower. So this is the first one, minimal energy rules. It's simple to understand. The second one, you heard about Pauli exclusion policy. What does that mean? Pauli exclusion policy means sublayer orbital. Sublayer orbital. I should say each sublayer orbital can be maximum occupied by 2 electrons spin opposite direction. So what that looks like? Very simple. If this is 1s, one goes down, one goes up, or up and down. It's the same thing. Who is Pauli? That's W. Pauli is a great physicist. He has 3 nationalities. He was born in Austria, got nationality from United States, and died in Switzerland. So Austria, United States, and Switzerland, 3 nationality. Why he's a great chemist and physicist? He was awarded Nobel Prize in 1945. In 1945, because of Pauli exclusion policy, and recommended, nominated by great Albert Einstein. However, he did not have a very long life, to 1958. Very smart people find that, okay? Third rules, we know this. Hund's rules. What is Hans rules talk about? Sub-layer orbital first occupied singly, or say singly occupied, before double occupied. This comes out with actually at the p layer. So if the p layer, what it looks like, we talk about the p layer have 3 sublayer orbital because of the Dunbar shape, have y-axis, x-axis, and z-axis. So what they should be arranged? They will be first singly occupied before double occupied. Go down, and go down. That's Hans rules. Hans is named by a great German physicist. This doesn't win any awards, okay? But I think it is important. But he have a very longer life. Well, was 3 years old. So it's very fair. People get Nobel Prize, 50, 80 years old, who didn't get anything, live a longer life. It's a joke, but you will remember that these 3 important rules and 2 important here is Pauli exclusion policy and the Hans rule. Okay, we talk about these. Looks like it's a little bit difficult. So let's give some of the examples to let you understand. Okay, some examples. First of all, let's do a carbon. 612. What should it looks like? Let's draw. 1 box, 2 box, and 3 box. Sublayer orbital. So what are they? 1s, 2s, and 2p. What it should be looks like the arrangement. Up, down, up, down. That is Pauli exclusion policy. Then we go 2p, up and up. Now why this is not a go here? Hans rules. They first singly occupied before double occupied. So what is this one we call? 1s2, 2s2, and 2p2. They add up together equal 6. Let's do the next one. Relatively easy. Nitrogen, 7, 14. What it looks like? Should not be difficult to do. Okay, you could do in your notebook. 1s, 2s, and 2p. So this will become up, down, up, down, up, up, and up. That becomes 1s2, 2s2, and 2p3. So those add up together equal 7. Next one, let's do another easy one. Oxygen. Okay, we draw it. Same thing here. So 1s, 2s, 2p. This is easy. Up, down, up, down. Here, 3 different sublayer. And we're going to go this way, and this way. Why we go those 3 first? Hans rules. Okay, then Pauli exclusion policy. Go down here. So what this one will be? It will be 1s2, 2s2, and 2p4. Okay, let's do a difficult one. Phosphate. 1531. Let's do a difficult one, okay. What's the electron gonna be looks like? That has to be 16. Okay, then let's draw it. This little bit difficult. 3, we're going to do here, maybe here. We don't know, so let's do it. 1s, 2s, 2p. What it looks like? Up, down, up, down, up, up, up. Then go here, we're going to do go down, and go down. That is added together is 10. Okay, then we go 3s. 3s we will do up, down. Then we go 3p. So we'll go up, 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 and then we go down. So what's the phosphates looks like? 1s2, 2s2, sorry, 2 is right here, and 2p6, 3s2, and 3p4. That's phosphate. Then we do a tricky one. Potassium. That's a tricky one, potassium. Always in a chemistry exam, we'll ask you potassium. What's the potassium should be writing about? Let's draw it. Okay. Okay. 1s, 2s, 2p. There is no problem here. This is, I'm just making it easy, okay? These all gone. So we do 3s, up and down, 3p, up, up, up. So we go down, down, down. How many we have already? This is 10. This is 18, is that right? We saw the 19. So this is 3d. And, sorry, this is 3s. SPD, sorry, 3d. And what gonna be this one looks like? Is 4s. Originally, we always think this is 19. This is add up together already 18. We think this should be 3d, is that right? However, it's at 4s. Why? It finds it is jumping. It jumps. People did not recognize it at the beginning. Lots of think it should be in the 3D sublayer orbital, but later on they're using chromatographer, kind of like a GCMS or HPLC we're using today, but it's not all the time. They see the morphology, they see the arrangement, they find the last one is at 4s instead of at 3D. Now, we finished talk about that. Looks like it is complicated. Then you will have a question for me. Why are you going to talk about this? Because there is two things we have to emphasize. It is on your slides, and all these material, what is added, because you have to understand about these two things. Number one, we have octet rules. Most of the biological activity atoms, their outer layer is always 8 electrons. The second thing is called the valence electron. What that means? In this very outer layer, that valence electron will be interacted with other electron to generate chemical bond. Therefore, the next question we want to talk about is major chemical bonds. Ian, you have to move this a little bit because it's not covered. So you're gonna, thank you very much. Move this a little bit. Just move the whole thing right there. If you can cover the whole there. Okay. So the chemical bonds. We want to talk about some major chemical bonds. We have three. Number one, ionic bonds. It looks like it's difficult to understand the ionic bonds, but I give you an example, you will be very easy to understanding, is sodium chloride. Okay, sodium chloride, you write Na plus Cl negative. What this means, the ionic bonds is basically attraction between positive and negative charge, or charged atoms, we can say that. So what is going to be looks like? Na plus, we call it sodium plus. This is actually loose electron. That's why it has become positive, and we call it cations. And the chloride, it is gain electron, become negative, we call it anions. And they connected with each other. If we are using so-called Lewis model, what will be looks like? This is somehow like this. Chloride have like 7 electrons in the outer layer. Sodium only 1. You can do a sodium by yourself. Okay, that's why you use cross express that. This is called Lewis model. Now the next question. Is ionic bonds a strong bond? Relatively strong, but not very. And I tell you one thing, there is something we will mention in the next week. Sodium chloride, if it is food grade, there could be working with electron, or working with water, going through electricity, and will generate sodium hydroxide and hypochlorite gases. This is one we treat as a cleaner. Hypochlorite acids, it is a sanitizer. We'll talk about that. This is we call electrolyzed water. This is widely used and approved to use to replace chlorine in the European countries, in the EU countries, due to post-harvest food decontamination. We will talk a little bit more next week. So the ionic bonds is the first bond. Second bond is covalent bonds. Covalent bonds. So what is covalent bonds? It is sharing electron. Instead of attraction, they are sharing electron. And a very good example is methane. Okay? So 4 hydrogen with, we had a carbon, and they could be combined, become a methane group. And this will be, if you want to join it, and they will be shared. But sometimes, their sharing capability are different. Some of them will be attracted electron more stronger than the other chemicals. Therefore, it comes out with a very important concept in the chemistry area, which is called electron negativity value. This is also basic chemistry. So H, we talk about C, N, and O. What are those electron activity values? H, 2.1, hydrogen 2.1, carbon 2.5, nitrogen 3.0, and oxygen 3.5. This comes out with a very interesting results. Some of these chemicals, their sharing electron is equal. Some of them are different. Therefore, we have two groups of the covalent bonds, which is non-polar and polar. Non-polar, obviously, they are equally sharing electron. If the bond is H to H, C to H, and C to C. How about the polar? Which means they are sharing electron, however, their attraction activity is different. There could be an N to H, N to C, O to H, and O to C. And I gave you a very easy example. That is our everyday life. Jessica is drinking a lot, is water, H2O. What it looks like. The O is right here, the H is right here. And there is an angle right here. This is about 104.5 degrees. There have this bond is covalent bond. However, the attraction of the electron are slightly different. The oxygen is much better than hydrogen, so we're using a delta to express about that. This is delta plus, and this is delta negative, and this delta plus. We will talk about this more later, okay? Now, a little bit of history. Who created the concept of negativity value? This is coming from a great American chemist. You know that, Linus Pauling, 1901 to 1994. A magic person. He wins 2 Nobel Prizes. The first one is 1952. For what? Sublayer orbital hybrid, especially sp3 hybrid. We will talk next week when we talk about water. And in 1965, he wins another Nobel Prize, is Nobel Peaceful Prize. Why? By the time he works with other chemists, physicists, together with Albert Einstein, to write a petition letter to Dwight Eisenhower to tell him, please do not use nuclear weapon in the war. So that's why he has 2 Nobel Prize, one for his major chemists, another one is for Nobel Peaceful Prize. And a dramatic person, and he had created this one, is a electron negativity values, and the sp3 hybrid. And we will talk about this later, okay? So a little bit of history about that. It's a very good life, 93 years old. I think he was born in Oregon and died in residence in California somewhere. Okay, so covalent bonds. And the next one, what we want to talk, is hydrogen bonds. Hydrogen bonds, everybody familiar about that. So what are the hydrogen bonds? You heard about this guy, is a DNA, double helix. And we know the gene-based complement policy is A complement with T, adenine complement with thymine, and cytosine complement with guanine. This is by a hydrogen bonds. And the hydrogen bonds is relatively weak. That is why the double helix of DNA could be separated. And another hydrogen bonds, you didn't realize it, but it happened in our everyday life, is actually in the water. So what happened is, we talked about this already. Okay, this is 104.5 degree. Water molecule, and this is covalent bonds. We just mentioned. Now, where is the hydrogen bonds? If you have another molecule of water, and this H is right here, then how they connected together? This is hydrogen bonds. Because hydrogen bonds is very weak, so that's why the water molecule could be break down and they could be moving. Now, how weak it is? They're using a thermodynamic value to evaluate it. The covalent bonds, if you want to break down, you need approximately 110 kcal per mole. And the hydrogen bonds, you only need roughly 5.2 kcal per mole. So this is more than like 20 times. That's why hydrogen bonds is relatively weak. So what is a hydrogen bonds based on this description? That means is a hydrogen, is a proton from polar atoms connected to an atom from a same or different electron negativity chemicals. This means atoms, okay, atoms. That is hydrogen bonds, relatively weak. Okay, so we finished talk about those three, which is the chemical bonds we introduced to you. The next one we want to introduce is a major biological function chemical groups. So Ian, can you check to see that the camera is covered by that?
Yeah, you can still see it.
You can see the side, okay? So what are those? Let's just give some of the examples, okay? The first one, everybody should be familiar. CHO. What is this? Aldehyde. Now, why we want to talk about that? Because later on, when we talk about the class, we will suddenly jump in those names. Let's say aldehyde, let's say ketone, let's say hydroxy. You may not be very familiar, so we're going to introduce you here a little bit. Aldehyde. Aldehyde widely existing in the aldose or carbohydrates. So a very typical example What is this? Glyceraldehyde 3-phosphates. That's glyceraldehyde 3-phosphates. This is a step after the aldolase break down fructose 1,6-phosphates and generate this guy during the middle of the glycolysis. So Thursday we'll talk about that. The second one is what is this? Carboxy group. Carboxy group is a major component of amino acids. Because of that, we have an amine group, and we'll give you an example. This is the amino group. This is the third one. The fourth one, what we have. This is, hydroxy group. Remember, the hydroxy group happened is in DNA. So, let's draw it briefly, not that complicated. And this here is OH, and this is H, this is H, and then CH2, and this with phosphates. This is 3', and this is 5'. We have to do is a replication go this way, is 5' to 3'. Why? We cannot do the other direction, because the other direction do not have a free available hydroxy bonds. So that's OH is a hydroxy bonds. Okay, we have another one we want to talk is this one everybody knows. That's called a ketone. So we will talk about the ketone CME when we go to the Maillard reaction. So that's a ketone. A good example for the ketone, and you should know that, which is CH3, goes CO, and then COOH. What is this? Pyruvate. Pyruvate acid. That's a ketone. What are the next one? How about SH?